Hello, good morning all. I hope you are doing well. Today we are going to start with eigenvalues and eigenvectors specifically for some special matrices like hermitian matrices, unitary matrices, and this is an important discussion and I hope you will learn a lot from this particular lecture. Let us start without wasting time. Okay, so in previous lectures we were discussing eigenvalues and we were discussing something called as your eigenvalue problem, right? So we were discussing eigenvalue problem. Okay, and this is an important topic I told you because most of the times in quantum mechanics we will be interested in the eigenvalue corresponding to the operator. So with this brief sketch, let us begin with whatever we have studied till now. Okay, so let us revise whatever we have studied. So till now we have studied that how to find eigenvalues, what are eigenvalues as such. Uh, we've seen that any eigenvalue equation is given by Ax is equals to lambda x. Here A is an operator and lambda is the eigenvalue corresponding to this operator. So what is lambda? Lambda is the eigenvalue corresponding to this operator. So this is the eigenvalue corresponding to operator A. Operator I should say, not I should not say operator right now. I'm saying corresponding to the matrix A. Okay, and quite many times, as I told you, we'll be interested in this particular quantity. We've we've also found that in order to find the eigenvalue, what do? We actually try to find a characteristic polynomial attached to it. So we actually find a characteristic polynomial attached to it. And how do we get that characteristic polynomial? We get this characteristic polynomial by determining this determinant, that is a minus lambda I determinant equal to 0. And once we determine this, we get a polynomial. We get a polynomial of a degree n. So we get a polynomial of degree n. And from this polynomial of degree n, by solving this, we get the roots, and those roots are nothing but the eigenvalues. So from these roots, we are going to identify the eigenvalues of the matrix A. Okay. Okay. So let us say I told you what is an algebraic multiplicity. So let us say that if this eigenvalue, this characteristic polynomial can be factorized in terms of its eigenvalues. Let us say this characteristic polynomial is given by Pt, and this is t minus lambda 1 raised to power n1, t minus lambda 2 raised to power n2, t minus lambda 3 raised to power n3, and so on and so forth. If let's say nk, I should write nk. So if this is your characteristic polynomial and let's say these are your eigenvalues, then these exponents are nothing but they are the algebraic multiplicity. So what is the algebraic multiplicity? So algebraic multiplicity of a corresponding eigenvalue, and algebraic multiplicity of a corresponding eigenvalue, let's say lambda I, is given by ni here. In general, by fundamental theorem of algebra, we also know that if there is a polynomial, at most it can have n real roots. So total number of eigenvalues can be varying from 1 to n. So at most you can have n eigenvalues in general, at most. Okay. They may be distinct, they may not be distinct as well. Also, we have discussed one specific case till now, and one of the specific case that I taught you was that for triangular matrices, whether it is upper triangular matrix or a lower triangular matrix, for triangular matrices, the eigenvalues are the diagonal entries themselves. are the diagonal entries. Okay, so for this and okay, we also studied that if all the elements of eigenvalue, all the elements of a matrix A are real, then it is not necessary. Then it is not necessary that eigenvalues will also be real. So it is not necessary that all the eigenvalues also be real. I hope till now all these things we have discussed. Okay, one more important thing that I need to mention here is that, let us say, one more thing, I think I have left it somewhere, but if I have not done it, let us do it here. If the eigenvalues of A, so I can write it here. So whether I take a matrix A or whether I take its transpose, the eigenvalues will not change. So just note it down. A matrix A and its transpose have the same eigenvalues. Eigenvalues. Have the same eigenvalues. The matrix A and its transpose have the same eigenvalue. It's fairly simple to see that. Okay, so for a matrix A, if I want to find the eigenvalues, then it is equals to determinant of A minus lambda I, right, equal to 0. And for its transpose, if I want to find, I'll write A transpose minus lambda I. Now whether you do this or you do this, they are one and the same thing. And always remember, identity transpose is identity itself. And since lambda is if lambda is a real number, so it's not going to change. So overall, this is equals to A transpose minus lambda I. So if I replace this here, what does it mean? So if I replace this here, I can write determinant of A minus lambda I whole transpose. So if whether I write this or whether I write this is one and the same thing. And what this will be equals to, always remember, whether you want to find determinant of A or whether you want to find determinant of A transpose, that is one and the same thing. So this is equivalent to finding determinant of A minus lambda I only. So what does it mean? It means that whether you want to find the eigenvalues of A or its transpose, they're going to be the same. Okay, but at times people get confused and they actually extrapolate this particular statement with regards to eigenvectors also. So kindly note that in absence of a symmetry, in absence of symmetry property, in general, you cannot relate the eigenvectors so I'm writing eigenvectors, please remember, okay? Eigenvectors of A and A transpose are not related. Please remember, they are not related. Okay, eigenvalues indeed are related, they are the same, but eigenvectors are not related. I hope it is clear till now. If anybody has got any doubt, please ask it here itself, and then we shall move ahead. I'm giving you a minute to think about all these things, and then we'll go ahead. Okay, so all these things are quite basic, and I have already stated all these things quite many times, but I just wanted to revise it because it was a weekly, you can say we actually did not meet yesterday, so we met today. Now further, uh, today we are going to discuss mostly the eigenvalue problem only with regards to some special matrices. And let us first take idempotent matrix. So let us first take the idempotent matrix. Just give me a minute. Let us first take the case of idempotent matrix. So what do you think the eigenvalues of idempotent matrix would be? So eigenvalues of idempotent matrix is either 1 or 0. So that is what I'm going to show you right now. Okay. So idempotent matrix. So here it is. It is at times also referred to as projection matrix. Okay. So when we are going to see it in our real analysis course, real analysis, sorry, linear algebra course for quantum mechanics, then as an operator, we are going to see that a projection operator is idempotent. So idempotent matrix and its eigenvalues. And its eigenvalues. So what is an idempotent matrix? Let A be a n cross n matrix such that A square is equals to A. Then this matrix is called as the idempotent matrix. So for example, let us take an example and understand. This is one of the example 1 1 and 0 0. So if this is an example, here clearly A is a non-zero matrix. Clearly A is a non-zero. It is clearly a non-identity matrix. Okay, but if you try to find A square, what you will get? You will get 0 1 0 1, and again you will get 0 1 0 1, and if you calculate, you will get, I think, 0 1 0 and 1. So basically you will get A. So clearly A is an idempotent matrix. So A is an idempotent matrix. Now let lambda be a eigenvalue for the same. So let lambda be the eigenvalue for this matrix. So I'm writing this would be a eigenvalue equation such that the column vector x is a non-zero one. So if column vector is a non-zero one, otherwise it doesn't make sense. Okay, so let column vector be a non-zero one. Now if I pre-multiply a both sides, what will I get? I'll get ax is equals to lambda ax, and what is this? This would be equals to a square. This would be simply a square x is equal to lambda square x, because ax would again give you lambda x. Since a square is given to be a, because A is an idempotent matrix, that implies Ax is equals to lambda square x. But we already know that Ax is equal to lambda x. That implies lambda square minus lambda x is equals to 0. However, this is not 0. However, x is not 0. What does it imply? It implies that lambda should be either equal to 0 or either should be equal to 1. So eigenvalues of idempotent matrix are 0 and 1. I hope it is clear. Okay, so I hope it is clear. Okay, so this was regarding idempotent matrix. Now think about nilpotent matrix. So we have studied nilpotent matrix, and I'm going to write it all over again. Here it is. What is a nilpotent matrix? Okay, so what is a nilpotent matrix? So a matrix is said to be nilpotent. So let's say n cross n matrix is there, and it is said to be a nilpotent matrix if a raised to power k is a zero matrix. So 0 is a n cross n null matrix. So if A is a matrix and such that A raised to power k is equal to a null matrix, then A is said to be the nilpotent matrix and k is said to be the order of nilpotency. K is called as the order of nilpotency. K is called as the order of nilpotency. Now, there is a very strong statement. I'm not going to prove this statement, but one half of this statement I'm going to prove, not the other half. Other half would require a rigorous derivation. But that statement is that a matrix is nilpotent if and only if eigenvalues of A are 0. Eigenvalues are all 0. A matrix A is nilpotent if and only if eigenvalues of A are 0. Okay, so that is the first thing that you should remember. Now you see, if I want to prove the other half of it, then I will have to take uh, uh, the help of a diagonal matrix, and then I can prove. But one half I can prove. But if and only if means what? If all the eigenvalues of A are 0. So what is the meaning of what is the meaning of this if and only if? See, if A is a nilpotent matrix, then all the eigenvalues of A would be 0. And if all the eigenvalues are 0, then it can only be a nilpotent matrix only. So this half I am doing, this half I am not doing, this half you have to accept. I am not giving a proof for here because that would be a rigorous proof not required, just remember it. Okay, but let us prove that the eigenvalues of a nilpotent matrix are 0. Okay, so that we can prove very easily. So that's something that I can do for you right now, because see, not because we are in physics, not many times you are going to prove it. Okay, but still, because you are starting this journey of mathematical physics, so I'm making it a habit that think about everything. See, I can do this also, but only point is that doing this would again take a good amount of time, and plus that you should know what is a diagonal matrix. So it's better that we should go one side only. So suppose A is a nilpotent matrix. Suppose A is a nilpotent matrix. What does it imply? It implies then there would exist certainly some k belongs to natural such that A raised to power k is equal to null matrix, and let lambda be the eigenvalue. So let the lambda be the eigenvalue of A. Now what I can do, I can simply write that Ax is equals to lambda x, isn't it? Now if I pre-multiply with A, it will give me A square is equal to lambda Ax, which is simply equals to what? It is equal to lambda square x. And if I keep it multiplying, what I will get? I'll get ak x is equals to lambda k x. Okay, so if I multiply it k times, I get this, and here. Okay, I hope it is clear. Now, as I have told you that if A is a nilpotent matrix with order k, with the order of nilpotency k, that implies k would be a null matrix. Okay, so it will be a null matrix, and also that if I think about this, it implies what? It implies lambda raised to power k x would be equals to what? It would be a null. What should I say? It should be a lambda raised to power k times x would be a n-dimensional column vector, n dimensional 0 column vector, right? And by definition itself, we know that for x is not equal to 0, x is not equal to 0, that implies what? That implies lambda must be equal to what? 0. Lambda must be equal to 0, because if x is 0, then we are discussing the trivial case. So we are not discussing the trivial case. So if it implies what? It implies lambda must be equal to 0. Lambda raised to power k must be 0. That implies lambda must be 0. So always remember, for nilpotent matrices, I am writing for nilpotent matrices, all the eigenvalues, all the eigenvalues, let's say matrix A, all the eigenvalues of A are 0. In fact, there would be a single eigenvalue only, that is 0. Okay, is that clear? I hope it is quite clear to you. Okay, so now let us move to something called as Hermitian matrices. And again, these are quite important matrices. Okay, these are very important matrices. So these are very important matrices. Why I am saying this? Because our quantum mechanics most will represent our operators in form of Hermitian matrices only. Okay, so let us start with an example of a Hermitian matrix. Okay, so what are Hermitian matrices? I told you that Hermitian matrices are those where A dagger is equals to A. Okay, if you remember that we have already done what are Hermitian matrices. Hermitian matrices are those matrices where A dagger is equals to A. Okay, that is something we have done. And what are anti-Hermitian matrices? Anti-Hermitian matrices are those where A dagger is equals to minus of A. So if A dagger is equals to minus of A, those are called as the Hermitian and A dagger is equals to A, then those matrices are called as the Hermitian matrices. One of the most profound examples that we are going to study in quantum mechanics would be the Pauli matrices. So Pauli matrices are examples of Hermitian matrices. Another example that I'm going to take today is from classical mechanics. Okay, so let us take an example from classical mechanics and of Hermitian matrices. So Pauli matrices I've already not explained you in general, but I have shown you in the previous lecture. Now let us take one simple example of if you remember that moment of inertia is a tensorial quantity. It is a tensor. So in general, we represent this in form of a 3x3 matrix. If you remember, so moment of inertia, I'm just defining it right now. We define it in terms of a matrix. Okay, I'm going to just write it. We are going to discuss all these things in quite detail as we are going to do classical mechanics. But right now, I want to show that the moment of inertia matrix is nothing but it is an example of Hermitian matrices. It is an example of Hermitian matrices. However, you'll find that since this is a classical mechanics thing, so the entries will not be a complex number. Okay, so whether you say a symmetric matrix or you say it is a Hermitian matrix, they are one and the same thing. But what is a moment of inertia matrix? If you remember, this is equals to this Ixx, here you get Ixy, here you get Ixz, here I write Iyx, here I write Iyy, here I write Iyz, here I will write Izx, here I will write izy, and here I will write izz. So this is my moment of inertia matrix. Okay, and in general, if I want to represent any of these elements, so I'll do it this way. I'll write ij is nothing but it is integral dm, and instead of r square, now we get this thing. All these things you are going to do in detail in classical mechanics, don't worry. And I'm just thinking that you might be knowing. Even if you're not knowing it, fine, I'm just representing it. Okay, I'm just giving it that each of these integral, each of these ixx, iyy, izz, whatever has been written, it can be encapsulated in form of an integral. Okay, so let us first try to find ixx. So what would be ixx? I'm just writing for ixx, I would be equal to j equals to 1. So if that is the case, this, and so I know that x1 I'm taking as simply x, x2 I'm simply taking as y, and x3 I'm simply taking it as z. So what would be ixx? Ixx would be simply dm. And what is this? This would be r square would be what? X square plus y square plus z square. What would be Kronecker delta 1 1? That would be equals to 1 minus of x square. So if I want to find ixx, it is nothing, sorry, it is nothing but it is equals to integral of dm y square plus z square. It is integral y square plus z square. Okay, and all other things you are going to get, don't worry. All other things you are going to get, no worries. What would be ixy? Ixy would be simply, so basically here I is equals to 1, j is equal to 2. So your Kronecker delta will go off. So you will get minus integral. You will have a dm, and then you will have a, I think I should write xy, right? Okay. Now let us take one example and try to construct a eigenvalue matrix. So consider a two-dimensional square. Consider a two-dimensional square of side A, and for simplicity, whose mass per unit area, let us say it is rho, is constant. So let us say that the mass per unit area is constant. Okay, so now it implies that the density is constant, right? So mass per unit area, sorry, mass per unit area, rho is constant. Now let us take the mass in general as m. I have already stated the side A. Now for a square, what do you think a small mass density would be? So small mass density, just let's say I'm writing it here. This small mass density would be what? This small mass density would be, this small mass dm would be in terms of the density rho dx into dy. Let us say we are talking in xy plane only. Let us say we are talking in xy plane. Okay, so this small mass would be equals to what? Rho dx dy. Right? And what would be rho? Rho would be simply total mass, let's say m divided by a square. Now let us compute the moment of inertia for this particular square. So what it would be, ixx would be given by integral 0 to a, and here you have rho is m upon a square, and there you will have y square plus z square, and then you will have a dx dy. You'll have a dx dy. I know that I'm on this xy plane, so clearly z must be equal to what? Z must be equal to 0. So if z is 0, then you are left with only y. So you are left with y. So y square would be there, and if y square is there, this dx would give you a. So I'm writing m upon a square into a, and what would be y square? Y square would give you y cube by 3, so it will be a cube by 3. So eventually, what you're going to have, m a square upon 3. So your ixx is m a square upon 3. Similarly, if you want to find I_y, what you will get, it is integral 0 to a, 0 to a, and then you have this m upon a square, and this is x square plus z square, and then you have this dx. I think it would be I_y, no? So I_y means what? So just writing it here. Okay, okay, so that is dx dy only. Sorry, no. So that is dx dy only. So I'll write dx and dy only. Okay, sorry. Okay, because we are in the like we are in the xy plane only. So if I want to write dm, this would be this only, rho dx dy only. Okay, I hope it is quite clear now. And what would be I_y? So again z is 0, so again we'll get m a square upon 3 only here. What would be I xy? It will be minus integration 0 to a, 0 to a, and I told you it would be xy, and then you will have a dx, and then you will have a dy. So if you do this, what you will get? You will simply get, and there would be m into a square as well, sorry, m upon a square as well. So now if you compute this, what you will get? I think x square by 2 and then y square by 2, so you are going to get m upon a square into a raised to power 4 upon 4, and a negative sign, so you will get minus ma square upon 4. And similarly, I'll what would be iyx? I think you can find it on your own. Iyx would be again minus of ma square upon 4 only. I mean, this is something that I'm leaving up to you. Now let us calculate izz. So what would be izz? It would be m upon a square integration 0 to a, integration 0 to a. I think it would be x square plus y square here, and then you will have a dx, and then you will have a dy. So if you integrate this thing, what you will get? I think if I integrate with respect to x, then I will get x cubed by 3, and then y square into x, and then again if I integrate with respect to y, so let me do it. So here I'll do it somewhere. So what I'll get x cubed by 3 plus x square y from 0 to a, and then integration dy from 0 to a. So what I'll get a cubed by 3 into a plus a square into this y would be what? Y square by 2. So it would be, I think, y square by 2. Okay, so eventually what you're getting a cube by I think this is a cube by a ki power 4 by 4, right? So this is a ki power 4 by 3, this is a ki power 4 by 3, and then this is, okay, so this is not the case. So izz what am I getting? So x square plus y square, x cube y x square dx. Okay, sorry, my mistake. So this is y square and this is x. Sorry. So if you do this, this would be a here, and this would be a cube by. Sorry. So what we are getting? I'm getting a. So I'm getting, sorry, this is m upon a square, and then multiplied by, I think this would be 2 a raised to power 4 upon 3, right? Okay, is that clear? So eventually I'm going to get 2 times ma square upon 3, and that was quite clear also from perpendicular axis theorem. You know that izz from perpendicular axis theorem, it is equals to nothing but it is equal to ixx plus iyy. So that is something that I'm not teaching right now, but okay, you should remember this also. So this is 2 ma square upon 3. And similarly, if you want to find different other things, let's say what would be zx, it would be simply 0, yz would be 0, izx would be 0. All these things would be 0 since we know that z is 0. So overall, if I want to construct a matrix I, the moment of inertia matrix for the square thing, what I will get? What would be ixx? So ixx was what? Again I have to move up. Ixx would be ma square by 3. So ixx would be ma square by 3. So I'll write ma square upon 3. What was ixy? Ixy, if you remember, it was minus ma square by 4. So it was minus of, I'm writing it here, ixy is minus of ma square upon 4. What was ix? It was simply 0. What was iyx? It was minus ma square upon 4. What was iyy? It was ma square upon 3. And here it was 0, here it was 0, here it was 0. And what was izz? It was 2 ma square upon 3. So if you want to calculate, if you want to take 12 common out, so I can write it in more convenient fashion. Ma square upon 12, if I take common out, what would be the entries here? The entries would be 4, minus 3, 0. I think minus 3, 4. Sorry, this I'm writing it here. 4 and 0. And then I'm going to get 0, 0, 0. 8. Now, if I do a Hermitian conjugation means what? I have to take a transpose and conjugate. I have to take a conjugate and a transpose. So all the elements are real. Since all the elements are real, so it does not make sense of taking conjugate, because conjugate would again mean the same thing only. So all the elements are real. So aij conjugate would be simply aij only. Okay, now if I want to take the transpose, what will I get? I'll get ma square. So I'm doing I dagger operation. So I've taken conjugation. I know all the elements are real, so it's hardly going to matter. This would be 4 minus 3 0. It would be minus 3 4 and 0. It would be 0 0 8. So clearly both of these matrices are same. So remember, moment of inertia matrix is Hermitian. So one of the example of Hermitian matrices, moment of inertia matrix is Hermitian. Okay. Another example from classical mechanics, if you remember, I'm just giving you a few examples so that you can relate it from your physics. So another example, I should take Lorentzian transformation. If you remember, because in quantum mechanics we've already stated that all the operators that we are going to study are nothing but Hermitian matrices only. I hope everybody is getting right. Harish is there, or anybody is there or not there? I don't know. If somebody is there, please let me know you are getting or not. So okay, we know that if we want to, if a frame of reference is moving with a relative, is moving with velocity v with respect to another frame, which is, let's say, s, then in this particular frame, if I'm trying to find the coordinates x dash, y dash, z dash, and in fact t dash as well, what these values can be written in terms of the values in this particular frame, that is x, y, z, t, is given by Lorentzian transformation. So you already know that x dash is equals to gamma times x minus vt. What is y dash? Y dash is simply y. If I'm moving along the x-axis only, z dash is simply equals to what? Z. And you know that t dash is equals to gamma times t minus of xv upon c square. If you remember, even if you don't remember, just remember them. Just take them as whatever I'm saying right now. Okay. So for example, I hope you must be remembering. If you're not remembering, fine. So this is something that we study in the special theory of relativity. Okay, in special theory of relativity. So if I want to express it in terms of the matrix notation, let us say I'm writing capital X dash, and here I'm writing L, and I'm writing X. What is L? L is the Lorentz matrix, you can say, Lorentz transformation matrix, you can say. Okay, and if I want to write it in this fashion, what it would be? It would be equals to x dash, y dash, z dash, and t dash. And what would be this L? L would be your Lorentz transformation matrix, and what it would be? It would be simply gamma, and I will write 0 0, and since here t is there, so I'll write iota gamma, I think v upon c. Okay, and here it would be 0 1 0 0, and here it would be 0 0 1 and 0, and here I have minus of iota gamma v upon c, and then 0 0, and then again gamma. Okay, and this x will be simply x, y, z, and t. Okay, so this is how you make. So this is your Lorentz transformation matrix, isn't it? So this is your Lorentz transformation matrix, and it is quite easy to see that this would be Hermitian. Just take a conjugate of it. So this will become minus iota, this will become plus iota, and then you take a transpose of it, and you are going to find that this particular matrix, Lorentz transformation matrix, is also Hermitian matrices. Is also Hermitian matrix. Okay, so all these things are quite important because probably they may be asked in your examination also, because most of the times we are so concentrated on whenever it comes to Hermitian matrices that we think that okay, Hermitian matrices, quantum mechanics, every operator is represented as a Hermitian matrix. So we tend to think in one direction only. I have given you two examples. One was actually nothing but a symmetric matrix. So obviously, if a Hermitian matrix if a matrix contains all the real elements, then whether you say it as a symmetric matrix or you say it as a Hermitian matrices, nothing matters. Okay, I hope it is clear. Okay, now we are going to discuss something regarding Hermitian matrices only. I think two matrices we have done. Idempotent matrix we have done, and we have done this also. Sorry, we have done idempotent matrix and we have done nilpotent matrix. Okay, and we have come to know that for idempotent matrix the eigenvalues are 0 and 1, and for the nilpotent matrix eigenvalues are 0. Now there is one important theorem, you can say, or you can say a property that I'm going to write for. So some important points I'm going to write down. Some important points I'm going to write down for your Hermitian matrices. So always remember that every Hermitian matrix, every Hermitian matrix can be written as what? As sum of two matrices B plus iota C, where C is a skew symmetric matrix and this is symmetric matrix, real symmetric matrix. Okay, both of them are real because I have introduced my iota here. So just remember that if your Hermitian matrix is there, let's say A, it can be written in terms of linear combination of your real symmetric matrix and real skew symmetric matrix. I think it is quite easy to see. Let me help you. I think I did not explain you that skew symmetric and symmetric, any real matrix can be written in terms of skew symmetric and symmetric, because that proof is quite easy to see. That was in even 12th standard. Let us try to prove this. So see, if a matrix is Hermitian, then I know that my A dagger would be simply A. What is A dagger? I'm again saying it is nothing but it is taking conjugate and then taking transpose. Basically, this is what it means by dagger. So A dagger is equal to A transpose, A conjugate transpose. Now, if I again take a transpose of this, if I again take a conjugate of this, what I'll get? I'll simply get A dagger, A transpose, sorry. If I again take a conjugate here, so if I'm again taking a conjugation here, I know that if I do a conjugate over a conjugate, I simply get A. So it would be A transpose and it would be simply equals to, and let us say, here I should write, let us say, okay, just give me a minute. Okay, so let us say that we are considering Hermitian matrix. So I have a Hermitian matrix A. So A dagger would be simply A. If I again take a transpose, if I again take a conjugate, what it would be? It would be writing A transpose here only, and it would be equals to A conjugate here. So if I take both side conjugate over conjugate is simply like A conjugate, again conjugate would be simply A. So that way it would be it. Now see, now I'm assuming two things. First thing is, let us assume that D would be equals to what? It would be equals to half A plus A transpose. This is and let us say C is equal to 1 upon 2 iota A minus of A dagger. Our claim is that this is symmetric and this is antisymmetric. So I am claiming that my B would be symmetric and C would be antisymmetric or skew symmetric. Okay. So in order to see that whether they are symmetric or non-symmetric, then what I can do this. B would be equals to what? I'm claiming, my claim is that my B is my claim is that B is my symmetric matrix. Let us see if I'm going to take if I'm going to take B transpose, what it would be equals to? It would be equals to 1 upon 2 A plus A conjugate transpose, and what I'll get, I can simply write A transpose plus this, and you know that A is your Hermitian matrix, right? A is your Hermitian matrix. So this particular thing will be what? This particular thing I can write A transpose A conjugate transpose. This is like writing A dagger only. So if I'm writing it as A dagger, I know this would be simply A. And what is A transpose? I know that A transpose for a Hermitian matrix will be A conjugate, right? Which is again equals to what? It is again equals to B only. See, so I can clearly say that B is a real symmetric matrix. Now what is my C? The first thing that you must be worrying that, see, I have written 1 upon 2 iota here and probably it may not be real. So let us first conclude that whether C is a real matrix or not. So for considering it, try to take the conjugate of it. So if I take a conjugate of it, I'll get 1 upon minus of 2 iota A conjugate minus A conjugate conjugate. And it is equals to, I think, what is A conjugate is what? A conjugate is simply okay, A conjugate will become, I think, A conjugate will become A, and this is A conjugate, and let us take this negative common, so this will become 1 upon 2 iota. So what we have got that C conjugate is simply equals to C. So if I'm doing conjugate of each of the elements, I'm getting C. So what does it imply? It implies C is a real matrix at first. Okay, is that clear? I hope it is clear. Please let me know. Okay, so if that is the case, now let us move a little bit further to prove that C would be a skew symmetric matrix. So C is what? C is equal to 1 upon 2 iota A minus of A conjugate, right? Now if I want to see the transpose of it, what would be a transpose of it? It would be 1 upon 2 iota A transpose minus A conjugate transpose. So it will be equals to 1 upon 2 iota. And what is A transpose? For A, don't forget, A is your Hermitian matrix. So A transpose will be A conjugate minus, this would be what? This is A dagger. So what I'm getting it is equals to minus 1 upon 2 iota A minus A dagger, and it is simply equals to minus of C. So I'm getting C transpose to be equals to minus of C. I'm getting B transpose is equal to P. So I can clearly see that, every Hermitian matrix can be written in terms of a real symmetric matrix and a skew symmetric matrix. So this is how I can write a Hermitian matrix A. So I can write a Hermitian matrix A in terms of a real symmetric matrix and in terms of a real skew symmetric matrix. This may be asked in your exam. In fact, you have studied that every real matrix can be written in terms of a symmetric matrix and an antisymmetric matrix. So similarly, I'm not going to prove it, I'm just writing it for you. Every complex matrix, so I'll write each complex matrix and let us say A n cross n can be written as A is equals to B plus iota C. Here B and C are Hermitian matrices. Here B and C are Hermitian matrices. Here B and C are Hermitian matrices. And what would be, so I'll write it here itself. Okay, so each complex matrix A can be written as A is equals to B plus iota C, where B and C are Hermitian matrices. Okay, this is something that I'm leaving it for you. It is quite easy to see. Okay, I'm going to give you a little bit of hint so that okay, so that you're going to take it from there. I think you can take it from there. Okay, so let us take an example and understand. Let us do it. Okay, let us once do it so that you're not able to you're not confused then. I mean, is that clear till now? Whatever I have written, is that clear at first? Let me ask. Is that clear? Okay. Chalo, let us move further. Okay. So sorry to have not seen that. Okay, so let us see. I'm just writing it here. Let us write B to be equals to what? Let us write B to be equals to A plus A dagger divided by 2. And let us write C to be equals to what? A minus of A dagger divided by 2i2. So remember, I'm doing the same. What I'm doing the same. I'm writing the I'm writing it in the similar manner in which, like, if you remember that every real matrix can be written in terms of a symmetric matrix and a skew symmetric matrix. In that fashion only, every complex matrix can be written in terms of a symmetric, in terms of Hermitian matrices B and C, and I have declared that these are the two such matrices, and it's quite easy to see that that B and C are Hermitian. So B and C are Hermitian. B and C are Hermitian. Because always remember, if I'm going to write A dagger dagger, if I'm doing A dagger dagger, it is equal to simply A. This is something that I'm leaving for you uh, to understand. A dagger dagger is equals to simply A. So if I try to take B dagger, what it would be equals to? It would be A plus A dagger divided by 2 and this whole dagger. So you'll get A dagger plus A dagger dagger is simply A divided by 2. So you're getting B. So B dagger equals to B means Hermitian. And if I'm doing C dagger, what I'll get? I will simply get, this would be first 1 upon 2 iota would be conjugated. So please do write, it would be minus 1 upon 2 iota. And this will become a dagger. So here it is a dagger minus A dagger. Dagger means simply A. And if I take a common out, so I'll get 1 upon 2 iota A minus of A dagger. So clearly it is equals to C. So C is also Hermitian, B is also Hermitian, and you can clearly see that B plus iota C would be simply A. So always remember, every complex matrix can be written in form of B plus iota C, where B and C are Hermitian matrices. So when it comes to complex matrix, it can be written in terms of linear combination of Hermitian matrices themselves. Okay, now comes the eigenvalue problem, and that is the most important thing that you should pay focus on. So okay, so now regarding the eigenvalue things, okay, so first thing that is very important is that the eigenvalues of Hermitian matrices are always real. So eigenvalues of Hermitian matrices are always real, and this is the reason that all the operators uh, in quantum mechanics we are going to see that they are Hermitian matrices, because if they are not Hermitian matrices, then the measurement which is quantified by the eigenvalues will be a complex quantity if it's not the case. So we know that the measurement should yield us some real physical quantity. So if, let's say, I am operating a Hamiltonian, then it should quantify me the energy eigenvalue. And if the energy eigenvalue is complex, it does not make sense. So in the formulation of quantum mechanics, the operators are represented as Hermitian matrices whose eigenvalues happen to be real. And it is quite easy to see. Um, I'm just giving you a brief proof for this. So if let's say I'm doing a Hermitian matrix, I'm writing HU is equal to lambda U. Here U is a corresponding eigenvector. So I'm writing U is a corresponding eigenvector. Now let us take on both side dagger. So I'll get HU dagger is equal to simply lambda U dagger. And what I will get from here, I will get U dagger. I will write H dagger, and here I will write lambda star, or you can say if you don't want to use star, I can use conjugate also. Sorry, I can use. If you're comfortable with star, so the lambda star I'm writing here, it implies conjugate, and it would be simply here U dagger only, right? And what is U dagger H? It will be simply U dagger into U dagger H dagger. So H dagger would be simply H, because we know that H dagger is equal to H for Hermitian matrices. So this is here lambda star U dagger. Is that clear? I think this is quite okay. This is quite easy to see. Now if I multiply both sides, so multiply both sides by a column vector U. Multiply both sides by a column vector U. So what I'll get U dagger H U is simply lambda star U dagger U. And always remember, this U dagger U represents the norm of U. So it cannot be 0. It cannot be 0. So let's say if I'm going to tell you, right, for example, let's say I'm doing this, and this would be your conjugate and transpose. So this will give you x1 square plus x2 square. We are not considering the trivial cases. So for non-trivial cases, it would be always greater than 0. So this particular quantity is non-zero. Now, if you think about this, this is one. This is one of the equation. I'm writing it equation number 1. And if I do the same operation here also, if I do the where it is. Okay, so we have multiplied it with U both sides, right? So I've got this where have I missed something? Okay, just let me know. Okay, I think I have missed something somewhere. I don't know. So this has given me lambda star U dagger U, and lambda star U dagger U is non-zero. Okay. Okay, so let me think about it. I think this particular portion can be written as lambda into U. So if this particular portion can be written as lambda into U, I'm taking lambda common out. This is U dagger U is equal to, okay, lambda star U dagger U. Okay, that implies that lambda star minus lambda. And what is lambda star? Lambda star is taking the conjugate of lambda times U dagger U is equal to 0. It implies what? It implies lambda star is equal to lambda. It implies that lambda is real. It implies that lambda belongs to R. So always remember, that the eigenvalues corresponding to the Hermitian matrices are always real. This is quite easy to see. Is that clear? I think it is clear. I think this is something that you all must have done in your BSc or MSc somewhere. Okay, so I hope it is clear. Now, if this is clear, then another important property is that corresponding to each of these eigenvalues, the eigenvectors that come are orthogonal to each other, and that is very important. This is supremely important because when we are going to see this thing, wave functions, the wave function can be written in terms of corresponding eigenkets. So corresponding eigenkets, we can write your wave function to be equals to. Okay, so these lambda i's are nothing but they are the orthogonal eigenvectors. So this is very important when we are going to see in quantum mechanics. So I'm writing it here. Once I'm writing it here, and as we are going to go for the quantum mechanics, I will take a few days for quantum mechanics. Okay, I'll take a few days, probably this week also, and probably the next half week also would be dedicated to linear algebra and formulation of quantum mechanics. So once you are done with the formulation, then quantum mechanics would be a cakewalk for you. Okay, so meanwhile, what I'll do in quantum mechanics, I'm going to run with some wave mechanics and probably some de Broglie hypothesis and all these things. So those topics which are which actually have led to the development of quantum mechanics, we'll discuss them. I think that would be fruitful to do that, and that will not even invoke the boredom here. Okay, so because quite a while we are doing only maths only, so it has been a week that we've been doing maths. Okay, so always remember, I'm writing it here. This is the fourth property that I'm writing for Hermitian matrices. The eigenvectors corresponding to the eigenvectors corresponding to the distinct eigenvalues I'm writing distinct, please remember. Okay, distinct eigenvalues of a Hermitian matrix are orthogonal to each other. Very important, supremely important. Now let us first understand what is orthogonality. So for example, when we were doing when we were small, when we were kids and we were doing scalar product, what does that mean? I mean that a dot b vector is equal to simply 0. Okay, if you are dealing with the dot product, then we know that if a and b are perpendicular to each other, then the a dot b is simply equal to 0. However, when it comes to saying it in context of column vectors, then I would say that if my column vector, let's say I take a column vector of n components. So let me take an n component. Let me take an n component column vector. Let me take an n component column vector, and let us say they are u1 and u2, and they are orthogonal to each other. Then it implies that u1 dagger u2 is equals to 0, and also u2 dagger u1 is equal to 0. So if the column vectors u1 and u2 are such that u1 dagger u2 is equal to 0 and u2 dagger u1 is equal to 0, then I will say that u1 and u2 are orthogonal to each other. Now let us think about this particular thing that I have stated. So if your eigenvectors corresponding to distinct eigenvalues, so let us say that lambda 1 is one of the eigenvalues whose eigenvector is u1, and lambda 2 is another eigenvalue whose eigenvector is u2. So what I have written? I have written that lambda 1 be one of the eigenvalues whose corresponding eigenvector is u1, and lambda 2 is another you can say another eigenvalue whose eigenvector correspondingly is u2. So this is your eigenvalue, this is your eigenvector, this is your eigenvalue, and this is your eigenvector. And I know that hu1 would be lambda 1 u1, and I know that h2 u2 would be simply lambda 2 u2. Okay. Now if I take a Hermitian conjugate on both sides, then what it will become? You will become u1 dagger h1 sorry, h dagger, and here you'll get lambda 1 star. I'm writing because most of the quantum mechanics book prefer to have a star. Otherwise, in maths we usually take a bar over it. It's one and the same thing, however. And here you have this dagger, and here also the same. So u2 dagger, h2 would be equals to lambda 2 star, and then you will have a u2 dagger. I think it's quite easy to see. Now see, already I've stated that H is a Hermitian matrix, and if H is a Hermitian matrix, then H would be simply, H dagger would be simply H. And also we have known till now that lambda corresponding to H are always real. So whether you take a conjugate or you don't take a conjugate, they are one and the same thing. So what I'll write, I will simply write that U1 dagger H is simply lambda 1 U1 dagger, and what is U2 dagger H? It is simply lambda 2 U2 dagger. Since I know that H is a Hermitian matrix, so I can write the same. Now what I can do, I can multiply here, what should I say? I can multiply this first thing to the right by U2. So I'm writing, I'll multiply this to the right by U2, and I'll multiply what I can say. So I'll multiply this by U2 to the right. So what I'll get, I will simply get U1 dagger H U2 is equals to lambda 1 U1 dagger U2. I hope it is clear. And what this particular thing would be, this particular thing H times H operated on U2 would give you, I think, lambda 2 U2, and it is equals to lambda 1 U1 dagger U2. And see, I have already stated that lambda 1 and lambda 2 are distinct. So that implies lambda 1 will not be equals to lambda 2. If that is the case, then it implies, sorry, if that is the case, then it implies lambda 2 minus lambda 1 times U1 dagger U2 is equal to 0. And since these both are not equal, it implies U1 dagger U2 is equal to 0. And similarly, if you take a conjugate of it, you take a dagger of it, you will get U2 dagger U1 is equal to 0. Hence, we can say that U1 and U2 are orthogonal to each other. Hence, U1 and U2 are orthogonal to each other. I hope it is clear to you. Okay, hence U1 and U2 are orthogonal to each other. Is that clear? So these are very important properties. That is why I gave proof to both of them. Otherwise, initial properties I would have even skipped the proof. Then also things would have worked. But still, I have given you because I have seen at times question at lower level exam, like for example JAM. These people ask such questions. So, but overall, at higher level, you may like for example, for if you're studying for net and anything, then these two eigenvalue properties are supremely important. These are supremely important. And with regards to diagonalization, also these are, I'm going to discuss a greater detail of diagonalization also later on. But okay, I hope this is quite clear. Now, just stating a property again. Just stating one of the. Okay, what is normalization? So this is something that we are going to do in quantum mechanics also. Normalization. So for example, I have already stated that if I'm doing U dagger U, so it will be positive only. If U is not a null column vector, let's say, again I'm showing it for you. Let's say this is your x1 and this is your x2. What would be U dagger? U dagger would be simply x1, this thing. This is how I can write. I have to take a transpose, so this row vector becomes a this column vector becomes a row vector, and then you have to take a conjugate. So this is it, and I know that U dagger U would be equals to what? It would be x1 square plus x2 square clearly greater than 0. So always remember that this is a positive quantity, and specifically we require at times that that this be equals to 1, and if this is equals to 1, we say that my U, that is a column vector, is normalized. I say that my U, which is a column vector, is normalized. Okay, so a set of column vectors which are mutually orthogonal to each other, I'm not going to write it again in further, but which are mutually orthogonal to each other, and you can say that, and um, and each of them can be normalized to unity, can be normalized to unity. This is what you call as your then we, let's say u1 and u2 are such that if I do u1 dagger u2, it comes 0. If I do u2 dagger u1, it comes out to be 0. And if I do u1 dagger u1, it comes out as 1. And if I do u2 dagger u2, it comes out as 1. Then this particular u1 and u2 are set to form an orthonormal set of eigenvectors. Orthonormal set of eigenvectors. They are said to form orthonormal set of eigenvectors. Okay, so these are called as the orthonormal set of eigenvectors. These are said to be orthonormal set of eigenvectors. Or in general, if I want to state that ui's and uj's form an orthonormal set of eigenvectors, then it implies ui dagger uj is nothing but it is equal to Kronecker delta ij. It is equals to Kronecker delta ij. So if your I is equal to j, then this is equal to 1, and if I is not equal to j, then it is equal to 0. So this is how you can express your orthonormality conditions. So I can express my orthonormality condition in this fashion. I hope it is clear till now. Now there arises a question that how to construct orthonormal set of eigenvectors. One of the standard approach, or you can say standard procedure, is called as the Gram-Schmidt orthogonalization process. Okay, I'm just writing it. This is something again we are going to see in detail later on, but just writing it for your knowledge right now. But I'm going to make you do a few more questions on this Gram-Schmidt orthogonalization as well. Okay, but right now, the process of construction of orthogonal eigenvectors, or you can say orthogonal vectors, can be Gram-Schmidt orthogonalization process or procedure. Just a brief of it I'm stating. I will do it for you in these things in a little bit detail later on. What this procedure is all about? This procedure is all about, let's say this procedure, this method is all about constructing. This procedure is all about constructing orthogonal vectors from where? By taking linear combination of a set of orthogonal vectors. By taking a linear combination of a set of orthogonal vectors. So what do I want to say? I want to say that let us say I already have two orthogonal eigenvectors. Let's say I already have, okay, so I already have two orthogonal eigenvectors. Let's say these are u1 and u2, and both are linearly independent. Orthogonal. Linearly independent means I cannot express u1 in terms of u2. Okay, so u1 and u2, let's say they form linearly independent orthogonal column vectors. They are nothing but they are orthogonal column vectors. Okay, now if this is the case, then I already know that u1 dagger u2 would be equals to 0, and I know that whether I take u1 dagger u1 or I take u2 dagger u2, it would be equals to 1. And simply I can also write that u2 dagger u1 would be 0 by taking a dagger here. Okay, so this is one thing. Now you see If I want to construct a set of what you can say, a set of orthogonal column vectors with the help of u1 and u2, one of the approaches is Gram-Schmidt orthogonalization process. Gram-Schmidt orthogonalization process, in which one of the eigenvector v1, which is the new eigenvector, can be written as simply u1, and another eigenvector v2 is nothing but it is equals to b times u2 minus I think this is u1 dagger u2 times u1. Please remember this. I'm not going to derive this. I'm just saying that if I have u1 and u2 as two linearly independent orthogonal column vectors, and if I want to construct a set of orthogonal vectors using these u1 and u2, then the set can be written as v1, which is equal to u1, and v2 is equals to this. I'm not deriving this. I can just do one help for you. I can at least confirm that these two form orthogonal vectors. That I can do for you. So v1 dagger v2 would be equals to what? It would be simply equals to b times u1 dagger u2 minus u1 dagger u2 u1, right? And I know that sorry, so this is one thing. Okay, have I missed something? Okay, and u2 u1 sorry, u1 dagger. Okay, so I'm writing it here, u1 dagger where it has gone. Okay, so I have written here, sorry, if I am I actually want to confirm that this is a orthogonal vector. So v1 dagger would be simply u1 dagger, right? Okay, and if I pre-multiply u1 dagger, so it would be u1 dagger u2 minus I think it would be u1 dagger, again a u1 dagger u2 and times u1, right? I think this is one thing, this is quite clear. U1 dagger u2, just give me a minute. U1 dagger u2, u1 dagger u2, u1 dagger u2 is one of the eigenvectors, right? And okay, if let us see once let me see. So I'm writing u1 dagger u2 u1. I can write it as u1 dagger u2 u1 dagger u1, and I know that u1 dagger u1 is simply 1, so I'm getting u1 dagger u2. So here it is u1 dagger u2 minus u1 dagger u2, and which is equals to 0. So clearly I can say that v1 dagger v2 is simply equals to 0. So I can say that my v1 and v2, here I'm writing v1 and v2 are what you can say are orthogonal to each other. Are orthogonal to each other. I hope you have got it. I hope you have got it. If you have not got it, please let me know. So this is sometimes referred to, this is referred to as the Gram-Schmidt orthogonalization process. Please let me know if you are getting it. If you are not getting it, I'll repeat it for you. Don't worry. So this is referred to as Gram-Schmidt orthogonalization. So what is Gram-Schmidt orthogonalization? Given two set of linearly independent orthogonal column vectors, let's say u1 and u2, which are normalized as well, then we can construct another column vector by the procedure as mentioned. Is that clear or not clear? Please let me know if there is any problem. Otherwise, I'll help you with some example also, so that you are able to understand. I think I made a mistake somewhere. I don't know. Just let me know. Just let me help myself. Just give me a minute, okay? Just give me a minute. Okay, so I think this should be some v1. Otherwise this will become 0 now. Okay, just give me a minute. Okay. In hurry, I have written something wrong. 1 minute. Just give me a minute. So just give me a minute. I think I should correct it somewhere. I think there is a mistake somewhere. Just let me. Just give me a minute. Okay. Just let me help myself with this thing. So what was Gram-Schmidt orthogonalization? So for Gram-Schmidt orthogonalization, we have actually two, because actually I was doing this and all of a sudden I thought ki if this is u1 u2 then it is equal to 0. Okay, just give me a minute. So what is the method? Method of constructing the orthogonal vectors by linear combination of a set of orthogonal vectors. So if u1 and u2 are two linearly independent orthogonal column vectors, if u1 and u2 are two linearly independent orthogonal column vectors, then what I can do, I can make another set of orthogonal vectors. So if u1 and u2 are given to us, then we can make another column of you can say orthogonal eigenvectors. Okay, this is one, and I think there would be something that I should be thinking about. Okay, u2. So I think I should write it all over again. Just give me a minute. I think otherwise you will get confused. Okay, you will get confused here. I think just give me a minute. So what is the procedure like? What we want to do? We actually want to write a set of a orthogonal eigenvectors using u1 and u2, which are also orthogonal to each other, right? We want to write a. Just give me a minute. I think I have made a mistake while doing something. एक मिनट रुकना. Just give me a minute, so that I'll confirm it meanwhile. I think this is just give me a minute. Orthogonalization. Okay. Okay, so what is a Gram-Schmidt orthogonalization? I've told you the Gram-Schmidt orthogonalization is to form a set of eigenvectors. It has to form a set of eigenvectors. Once you know what set of eigenvectors, orthogonal set of eigenvectors. Once you know two of them, let's say u1 and u2 are let's say u1 and u2 are two linearly independent orthogonal column vectors, and you want to, and what is linearly independent orthogonal column vectors? u1 dagger u2 would be equal to 0, u1 dagger u2 would be equals to u2 dagger and u2 dagger u2, and this is equals to simply 1. And using these u1 and u2, using this u1 and u2, if I want to construct another set of orthogonal vectors, then v1 is simply equals to what? u1. v1 is simply equals to u1, and another set of eigenvector which is equals to v2, it is equals to, let us say, some constant times, I think it should be u2, that is absolutely fine, minus I should write here, what should I write here? I think it should be, okay, let me help myself. I think there is some error in this, and that is why I'm getting stuck. Just give me a minute. Meanwhile, I'm trying to figure out. Okay, so as much as I remember, okay, just give me a minute. I'll do it for you. Because if it is u1 dagger u2, then I think there will be a problem. That's why I'm getting confused. Just give me a minute. Okay. Okay, so I think here we should have, just give me a minute so that I'll be able to help you here. Okay, otherwise it will be okay. So let me help myself. So you can say that there is a, you can say that there is a, you can say right now that there is a process right now. Just remember that. I'm just writing it here. I'll find this particular thing out and help you out, because actually when I was writing this u1 dagger u2, then I thought that, oh, u1 dagger u2 is already 0. Then what am I doing? So as much as I remember, it should be equals to, um, I think it is, when I write it in terms of that would be it. But okay, let me, for right now I'm skipping it, and I'll let you know in a minute or so. Okay, in a minute or so. So let me skip this and let me write a few other properties. Now see, if till now we have seen what? Till now we have seen that eigenvalues of Hermitian matrices are real, and we've seen that the eigenvectors corresponding to the eigenvalues form a orthogonal set of vectors. They form an orthogonal set of vectors. Okay. Now, I got actually confused in this particular thing. I'll help you in just a minute. Meanwhile, I'm just writing a few more properties, and the properties number 4 or 5 or 6. Okay, 6 number property would be, if an eigenvalue lambda of a Hermitian matrix, if an eigenvalue lambda of Hermitian matrix, let's say it has a multiplicity r, it has a multiplicity r, let's say it has a multiplicity r, then what I can say, then there exist r linearly independent eigenvectors corresponding to lambda. Now what is the beauty of it? See, what I told you, that if a matrix is Hermitian, let's say if a matrix is Hermitian, let's say this is your Hermitian matrix H of n cross n, then there are two possibilities. One of the possibilities is that they have a distinct eigenvalues. Let's say they have distinct eigenvalues. If they have distinct eigenvalues, then corresponding to each of these eigenvalues, the eigenvectors which are created, they are nothing but they are orthogonal to each other. Good enough? Now it may so happen that there are some common eigenvalues. Let's say there are some eigenvalues which are repeated, and let's say they are repeated r times, and other are, let's say, n minus r, so corresponding to these n minus r distinct eigenvalues, there would be eigenvectors, and these eigenvectors are also orthogonal. And the theorem states that even if there are eigenvalues which are same, like if there is eigenvalue which is a multiplicity of r, then even these have distinct eigenvectors. In fact, these are linearly independent distinct eigenvectors. So overall, always remember that corresponding to a Hermitian matrices, even if the eigenvalues are distinct, or even some of the eigenvalues have some multiplicity, overall the eigenvectors arising out of them would be orthogonal to each other. I hope this is something that I have made it clear to you. Okay, I hope it is clear. Gram-Schmidt orthogonalization, don't worry, I'll let you know. Don't worry. Just give me a minute, I'll let you know. Actually, I'm getting confused with U1 and V1. Otherwise, it's all fine. But overall, please understand. Okay, till now everybody has got the point. Okay, now you see, in general, till now I'm writing that are linearly independent eigenvectors. Okay, now more bolder statement I'm writing, and that bolder statement is that overall overall, all these things, if I have to conclude, I have to conclude that the eigenvectors of n cross n Hermitian matrix, eigenvector of n cross n Hermitian matrix forms a set of n orthonormal eigenvectors. Now this is the beauty of it. See, what I want to suggest that, let's say, if first what I wrote in before this particular Gram-Schmidt orthogonalization, what did I write? So the first thing that I wrote was that if the eigenvectors corresponding to the distinct eigenvalues of a Hermitian matrix are orthogonal to each other. So if the eigenvalues are distinct, then the eigenvectors are orthogonal to each other. Okay. Now, further, if I state that if an eigenvalue lambda of a Hermitian matrix has multiplicity R, then also there exist R linearly independent eigenvectors. In fact, these independent eigenvectors would be orthonormal to each other as well. So I also write that n are linearly orthonormal independent eigenvectors. Okay. So what did I write? So I wrote that even if the eigenvalues are distinct, corresponding to them the eigenvectors will also be orthonormal as well. Orthogonal means what? U1 dagger U2 would be equals to 0. And what is orthonormal? Additionally, if I do U1 dagger U1, that is also 1, and U2 dagger U2, that is also 1. So orthogonal, and here also orthogonal, instead of orthogonal I can write orthonormal. So that is something that I'm going to show you by examples also. Okay, orthonormal. So what is happening? Even if the eigenvalues are distinct, then also I am getting orthonormal set of eigenvectors. Even if the eigenvalues are having multiplicity, then also I am getting distinct eigenvectors which are orthonormal to each other. So in totality, I can write that if I have an n cross n matrix, if I have a n cross n matrix which is Hermitian, then it forms a set of n orthonormal eigenvectors. Please remember this. I hope it is clear. Now see, I hope it is clear till now. Is that clear or not clear? Please let me know. Okay, so I will write that also. Gram-Schmidt orthogonalization also write. Actually, that is a bit of a diversion from the topic. So actually, I got a bit diverted, and then actually I forgot what to write. Actually, it is in my mind, but I'm just not able to recollect it. So I'll write it here. Don't worry. But you have understood the algorithm now. So Gram-Schmidt orthogonalization is a algorithm by which, if I know two linearly independent orthogonal column vectors, I can create a set of another orthogonal column vectors using some scheme. And this scheme actually I just got skipped somewhere. So I'll just help you out here. But overall, please remember this. Okay. Now you see. Okay. Now you see that. What is a symmetric matrix? Symmetric matrix, after all, is what? Symmetric matrix is nothing but it is a special case of Hermitian matrix only. Special case of Hermitian matrices only. So whatever result that you've written till now for Hermitian matrices are true for symmetric matrices also. After all, you know that Hermitian matrices are what? Hermitian matrices, if I say that in a Hermitian matrices all the column entries or all the row entries or all the entries are real, then they are nothing but they are real symmetric matrix, right? So all these results apply to the symmetric matrices also. But additionally, one of the statement that you should remember for symmetric matrices, additionally for additionally one of the statements I'm writing for symmetric matrix, I'm writing one of the statement. Please remember this. There's one of the statement and which suggests that what should I write? I should write every eigenvector of a real symmetric matrix, every eigenvector of a real symmetric matrix can be chosen real. So there is an additional freedom to us in real symmetric matrix that every eigenvector of a real symmetric matrix can be chosen real. Okay, so let us try to think about it. So if I have a symmetric matrix, let's say S, when it applies to lambda x, then it gives me lambda x, right? And we know that for a symmetric matrix, the eigenvalues would be real. That is quite clear because I told you that symmetric matrices are nothing but they are special cases of Hermitian matrices only. Those eigenvalues of symmetric matrices are real. Now what I'm going to do, I'm going to take a conjugate. So it will give me lambda star, and this is, and I know that lambda star is simply lambda, so this is it. Okay, now you see, since S is symmetric, real symmetric, so I can write that S is equals to S star. Because since S is symmetric now, real symmetric matrix, so S is equals to S star. So here it is 1, I think. Here I can write it as 2. And what is X? X is the eigenvector corresponding to this lambda. X is eigenvector corresponding to lambda. Okay, so what I'll get S x star lambda x star. So what I have got here, I can say that X is the eigenvector corresponding to lambda. Even X star is also eigenvector corresponding to lambda. From this, you can see S x star lambda x star. So you can say that if X is the eigenvector corresponding to lambda, X star is also eigenvector corresponding to lambda. And in fact, what you can do, you can add these two up. So what I'll get, S x plus x star is equals to lambda x plus x star. And let's say you know that let's say entries are ai's and plus let's say bi. Let's say these are kind of entries you have. Okay, then what would be x star? X star would be simply iota ai minus iota bi. And if you add them up, what you will get? You will get only real things. So since we know that x plus x star is real, what does it imply? That you have chosen an eigenvector, let's say this is y, which is completely real. So corresponding to a symmetric matrix, you can always choose an eigenvector which is completely real. I think it is quite clear to you, and if it's not clear, please let me know. Then we are going to do some questions regarding Hermitian matrices. I hope it is clear till now. Please let me know if there is something that you're not following. Now we'll do a few questions and then we will move ahead. Is that clear or not clear? Please let me know. Okay, so I think everybody has got it. Okay, so till now everybody has got it. Now see, so always remember, so these are some properties. Let us revise them up and then we will do the questions for the same. So today we started with a few more new special matrices by some name that are and we wanted to actually investigate the eigenvalues property for the special matrices. So one of the special matrices I started the lecture was idempotent matrix. For an idempotent matrix, always remember the eigenvalues are simply 0 and 1. Okay. For a nilpotent matrix, the eigenvalues are all 0. Okay, please remember this. Then I further moved on to something called as your Hermitian matrices. So if you are considering Hermitian matrices, all the eigenvalues to the Hermitian matrices are always real. In fact, there is a bolder statement which suggests us that eigenvectors corresponding to all of these eigenvalues are orthogonal to each or orthonormal to each other, in fact. Okay, and also that we studied that every Hermitian matrix can be written in form of a linear combination of real matrix, real symmetric matrix and a skew symmetric matrix. And in fact, each complex matrix can also be written in terms of Hermitian matrices. Eigenvalues of Hermitian matrices are always real. Eigenvectors corresponding to these distinct eigenvalues of a Hermitian matrix are orthogonal to each other, in fact orthonormal to each other. Also remember that even if they are not distinct, let's say there are r eigenvalues, there is an eigenvalue which is repeated r times, then corresponding to that eigenvalue which is repeated r times, you have r linearly independent set of eigenvectors which are again orthonormal to each other. So overall remember that if you have an n cross n Hermitian matrix, then you can have n linearly independent orthogonal, in fact you can make them normalized also, orthonormal set of eigenvectors. This is extremely important for your quantum mechanics. And actually I stated one thing, I'll confirm it tomorrow, but actually I stated one of the you can say procedure in order to write the you can say orthogonal column vectors. So if you have two column vectors given by u1 and u2 which are you can say orthogonal to each other, then you can always construct a set of orthogonal column vectors using something called as Gram-Schmidt orthogonalization. So let's say you have u1 and u2 as linearly independent orthogonal column vectors, then you can always construct another set of orthogonal column vectors by Gram-Schmidt orthogonalization, where v1 is equal to simply u1, and if I remember, I'll confirm it for you tomorrow, then v2 is equals to, b is like any constant that obviously I can normalize it, fine. This should be u2 minus of I think I should write it u2 dagger here, u2 dagger v1 times v1. I will have to see it, but right now I have written it. Right now I have written this u2 dagger u1 times v1. I will also urge you to confirm this particular thing, and if you confirm this particular thing, then I think it will be good for me. I think this should be it, but otherwise because whatever I wrote was a little bit, I thought it is not right. When this is what I thought, because okay, so this is what I think right now. We'll see it tomorrow also. We'll see it tomorrow. Okay, and also that it makes more sense where we are going to do inner product spaces, then it is quite convenient for us to write. Okay, so there it's not a worry. Okay, again that I told you, if an eigenvalue of a Hermitian matrix is there, lambda, then even if it has a multiplicity r, what do I mean by multiplicity r? Let's say if your eigenvalue is repeated r times, so let's say you're in characteristic polynomial, you get this kind of stuff, that is t minus lambda raised to power r. Then corresponding to each this particular eigenvalue lambda, there are independent. How many independent? There are r independent eigenvectors. Okay, these are r independent eigenvectors which are again orthogonal to each other. Again, orthogonal you can see orthonormal also, because you see always normalize a column vector, isn't it? So for example, if you have a column vector x1, x2, You can always normalize it. You can always normalize it by dividing it by 1 upon x1 square plus x2 square. You can always normalize it to unity. So that is why always remember that if you have an n cross n Hermitian matrix, then it always forms a set of n orthonormal eigenvectors. Please remember, this is very important when it comes to quantum mechanics also. And now additionally, for a symmetric matrix, I have written every eigenvector of a real symmetric matrix can be chosen real. So here I have shown you that if I have a eigenvector x, then Sx would give you lambda x. I have taken a conjugate, then S star x star lambda star x star. Since S is real symmetric, then S star would be simply S. Sx star would be lambda x star because lambda is real. So lambda star would be simply lambda. And you can see that x star happens to be an eigenvector of lambda. X is also an eigenvector of lambda. If you add them up, this is another new eigenvector. You can see that Sy is equal to lambda y. So this particular thing, I know that x plus x star would be what? It will have only real entries. So for corresponding to every symmetric matrix, you can always have a real eigenvector. So you can always choose a real eigenvector. I hope it is clear till now. Okay. I have written whatever I could write for Gram-Schmidt orthogonalization. I leave it on you to check it out. And if you find that there is an error, kindly let me know in the group. So, although I will do it again in the inner product spaces, so don't worry about it. I just wanted to convey you that there is a method in order to generate a set of linearly independent orthogonal eigenvectors. So that is what was my I think thought, but actually somehow I don't remember that. I just forgot. Okay, fine. However, I have written that up. So now let us try to write. Determine some eigenvalues questions, and then we will go to unitary matrices. Okay, so we want to determine the eigenvalues for this Hermitian matrices. This is 0, iota, 0, iota, 0, minus iota, and then you have 0, iota, and 0. Okay. Now try to determine eigenvalues for this matrix. So let us say this is H. Try to determine me the eigenvalues. I am waiting for you. Please write in the comment section what would be the eigenvalues for this. Please, that is something that I want you to do. Just do it. Okay, so I hope eigenvalues people would have got. Please in the comment section write the eigenvalues if you've got the eigenvalues. This is a simple question. That is why I'm leaving it for you. Okay, 0 plus minus 1, good. So okay, so this is right. So eigenvalues that you've got must be -1, 1 and 0. -1, 1 and 0. Okay, it's quite easy to see. What I wanted to convey that whenever you are trying to find eigenvalues, don't forget this this 1 upon root over 2. Basically what students do, they forget this. So always try to write it in this fashion. So if I'm writing h minus lambda I equal to 0, then it should be this way. It should be minus lambda minus iota upon root 2. Don't forget this 1 upon root 2. At times you forget it, then you're going to get wrong answers. So please don't do that. Okay, here it would be 0, iota upon root 2 and 0. So this is quite often people make this mistake. So please don't make it. So now if you, I think this is something that you can do on your own. That's why I'm not doing it for you. So you'll get eigenvalues equals to lambda is equal to exactly whatever the students Anshul and Rajat have written. It would be 0 and plus minus 1. Now corresponding to these eigenvalues, we can always have eigenvectors. And let us now test our theory. Because see, whatever theorem I have given to you, I have not proven for you. So now let us test our theory. So let us test our theory. What was the theory? Corresponding to these eigenvalues, the eigenvectors which are created are orthogonal to each other. Don't get confused with orthonormality. Normality means what? You can only normalize it. So I can say that corresponding to these eigenvalues, I can always need the eigenvectors which will be forming will be orthonormal to each other. Will be orthonormal to each other. Let us see that, so that your theory is tested. So as suggested, let us first do for the lambda is equals to x. So let us do for lambda is equal to 0. Sorry, lambda equal to x, lambda equal to 0. Let us take it for lambda equal to 0. So for lambda is equal to 0, what you are going to have, this would be 0 minus iota upon root 2. This would be 0. This would be iota upon root 2. This would be simply 0. This would be minus iota upon root 2. And I think this is 0. And this is iota upon root 2. And then again this is 0. So instead of lambda, I have written 0. And let us take column vector x1, x2 and x3. If I take this as a column vector equals to 0, if I do, what would I get? Okay, what would I get? So if I do this x2 is going to be 0. Clearly x2 you can see 0 from the first equation itself. If you do this, you're going to get x2 equal to 0, and you can write that iota upon root 2 x1 is equals to iota upon root 2 x2 x3, sorry. So clearly x1 equal to x3. So the column vector that you're going to get corresponding to lambda equal to 0 would be 1, 0, 1. And what if you want to normalize it? You can normalize it by dividing it by root over x square plus x3 square. Is that clear? I think this is quite clear. I think you can normalize it. Normalizing it would be what? Normalizing it is nothing but actually taking a, because this is real only, no? Sorry. This is real only, so you don't have to take a, even if you take a conjugate, it is going to be one and the same. You take 1, 0, 1 and multiply 1, 0, 1. You will get simply, I think, 2 and take a root over of it. So this is how you do. So this is your normalizing constant. So I have divided it by 1 upon root 2. Okay, I hope it is clear. If you want to do it, actually, I can do that also. Chalo, I'll do it. Probably people will not. So what we do actually, so I'm writing it here, so that if somebody is not knowing, we actually multiply our eigenvector with some constant. Let's say not lambda, let's say c. So what it would be equals to c times 1, 0, 1. Now this is what, this is your normalizing constant. What I'll do, I'll multiply c star 1, 0, 1 to c 1, 0, 1 and equals to 1. So basically what I'm doing, this is your eigenvector and normalizing it. So for normalizing it, I have to do dagger u should be equals to 1. So here I get c mod whole square, and here this would be equals to 2 equals to 1. So that implies your c1 is equals to 1 upon root 2. So if you multiply c1 as 1 upon root 2, this is like equivalent to writing the, it is equivalent to normalizing it. Okay, it is equivalent to normalizing your column vector. I think this is quite simple, but okay. Okay, so lambda equal to 0, I have got an eigenvector. For lambda is equal to, for lambda is equal to 1, let us try to find eigenvector. It would be minus 1, iota upon root 2, minus iota upon root 2, 0. Here you have iota upon root 2, here you have minus of 1, then you will have minus iota upon root 2, then you will have 0, you will have iota upon root 2, and then you will have a minus 1, instead of lambda I am writing minus 1. Now here you have this x1, x2 and x3 equals to 0. Now from this equation you can clearly see that minus of x1 and minus of iota upon root 2 is equal to x2. So from here you can clearly write that your x1 would be equals to minus of iota upon root 2 x2. So if you choose x2 as 1, your x1 would be minus iota upon root 2. And from the last equation, this from here, if you conclude, what you will get? You will get your x2 times iota upon root 2 minus of x3 is equal to 0. So that implies what? That implies your x3 would be equals to x2 times iota upon root 2. So if I want to write corresponding to this lambda equal to 1 eigenvector, what would be the eigenvector? The eigenvector corresponding to this would be, I am writing it here. So corresponding to lambda equal to 1, the eigenvector would be, okay, normalizing is okay, okay. So sorry. Actually, I think that many people from JAM also, if they are attending, then they will not be able to get. So that's why I keep doing things very simple also. Okay, I understand. Minus iota upon root 2, and here you will have a iota upon root 2. So this is the column vector corresponding to lambda equal to 1. This is a column vector corresponding to lambda equals to 1. Is that clear? And again, if I want to normalize it, I can normalize it. This iota root 2, this would, I think the normalizing constant will be 1 upon root 2, because don't forget, you have to take a this is how you do. So if I take iota upon root 2 mod, this would be 1 upon root 2 square, that is 1 upon 2, 1 upon root 2 square, 1 upon 2, and 1 square is 1. So 1 plus 1, 2, and 1 upon root 2. So this will be it. And corresponding to lambda equals to minus 1, lambda is equal to minus 1, the eigenvector would be, I am writing it directly, I think it would be 1 upon root 2, iota upon root 2, and here it will be 1, and here it will be minus iota upon root 2. Just remember this. So let's say this is your lambda 3. So corresponding to this you have x3. Let's say this is your lambda 2, that is lambda 2 is I think 1, for which you have an x2, and you have a lambda 1 for equals to 0, for which let's say your column vector is 1 0 1 and this. Okay, so now I'm going to write it below for all of them. So given Hermitian matrix, for given Hermitian matrix H, we have 3 eigenvalues, that is lambda is equal to 1, lambda is equals minus 1, lambda is equal to 0, and lambda is equal to 1. And corresponding to these 3 eigenvalues, we have the eigenvector given by 1 upon root 2. I'm just verifying the theory for you. The eigenvector would be iota by root 2, there would be 1, and there would be minus iota upon root 2. Then again, for lambda is equal to 0, you had I think 1 over root 2, 1, 0, and 1. And here I think 1 upon root 2, and the sign difference was there. I think there was minus 1 upon root 2 here, and here was 0, and here it was iota upon root 2. Now you just verify at least for these two things that they are orthogonal to each other or not. So we have already normalized it, so there is no doubt regarding the normalization thing. So if I write orthogonal, then it would mean orthonormal, because we have already normalized them. So if you just take these two also, let's say this is your x1, let's say this is your x2, and let's say this is your x3. If I take x2 dagger x3, what I will get? I will get 1 upon root 2, and this would be 1 0 1, and then you have this 1 upon root 2 here as well, and this will be minus iota upon root 2 0 and iota upon root 2. What you will get? You will get 1 upon 2 minus iota upon root 2 plus iota upon root 2, and this is simply equals to 0. So clearly you can get that x2 dagger x3 would be 0. If you want to see what would be your x2 x3 dagger x2, this would be again 0. See, this would be 1 upon root 2, this would be iota by root 2, this would be 0, and this would be minus iota upon root 2. If you multiply it by 1 upon root 2, 0, and 1 upon root 2, what you will get? You will simply again get 1 by 2, and here you will have iota upon root 2, and then you will have minus iota upon root 2. Again you are getting 0. So please remember, this I think you can verify on your own self for x1, x2 and x1, x3. This is leaving it to you as a homework. Okay, so always remember the crux of the matter for Hermitian matrices is, one, that the eigenvalues are real. Second, the eigenvectors corresponding to the eigenvalues are orthogonal. Third, for a Hermitian matrices, whether eigenvalues are getting repeated or they are distinct, the eigenvectors corresponding to the eigenvalues will always form a set of n linearly independent orthonormal vectors. Please remember this. Okay, what is the difference between a symmetric matrix and what is an additional thing that you can write for symmetric matrix? An additional thing that you can write for symmetric matrix is that for a symmetric matrix you can always choose an eigenvector which is completely real. So these are some of the things that you should remember. I hope it is clear till now. Okay, now we'll do a few more questions and then we will terminate this lecture, and we'll do unitary matrices tomorrow. Okay, so that you are also then okay. So I hope till now everything it is clear. I know I'm going a little bit slow, but I'll increase my pace from tomorrow. Okay? I'll increase my pace from tomorrow so that we'll do more questions then. So I hope it is clear till now. Now let us do unitary matrices also, so that we are not able to. So I think I want that somehow. Okay, let us do one important thing from our you can say physics side. Okay, let us do that also. So you'll enjoy something, that you are doing some physics thing. Okay, otherwise you'll get bored. Okay, so now let us take an example from physics. Let us take a vector classes. Yes, I'm starting vector. Probably vector means what? I mean vector spaces, do you mean? Okay, so so let us start with what I was saying. Let us start with something called as spin matrices. Okay, so there is a term, or you can say there's a quantity which has got no classical analog, and that is spin. Spin is a quantity which is inherent to quantum mechanics only, and spin angular momentum operator S. Okay, spin angular momentum operator S happens to be a Hermitian operator. If you don't relate to the term operator, you can take it as Hermitian matrix for right now. Okay, so so for spin half particles like fermions, like electrons, for example, for spin half particles, let's say for electrons, I'm saying the Cartesian components Sx, Sy, and Sz are represented by a 2 cross 2 matrix. So they are represented by a 2 cross 2 matrix. And what are those? Sx you can write. I'm just giving you. I mean, this is something that we are going to do, but just explaining you the matrices. So this is 0, 1, and 1 and 0. Sy would be what? It would be simply h ket by 2, and then you have 0 minus iota, and you have this iota and 0. And what would be sz? Sz would be simply h ket by 2, and then you have this 1, 0, 0, and minus 1. Okay, so these are three matrices. You can take them as matrices. I have given them the background for the same. If these are the matrices Sx, Sy, and Sz, then what would be the eigenvalues corresponding to this? And please remember, if you remember, The same structure did you not see in your poly matrices? So you can always say that if I want to write my S, then I can always write it is nothing but it is equals to h cat by 2 times sigma. So basically this is how you can relate your spin matrices, that is Sx, Sy and Sz, with your poly matrices. This is something that I have stated very initially in the lecture. So I have already stated that these matrices, that is the Pauli matrices, are nothing but they are Hermitian matrices. This is something that you can verify on your own, and I have verified it quite many times. Now let us try to find the eigenvalues. Let us try to find the eigenvalues. Let us try to find the eigenvalues. Okay, so let us try to find the eigenvalues. So these are very important. So eigenvalues, if I want to find, I know that, let's say start from z. So Sz minus lambda I modulus equals to 0. This is quite easy to see that this would be equals to what? It will be equals to, here it is. So h cat by 2. So it will give you, I think, it would give you, I should write it somewhere so that. So Sz minus x, so I'm writing it h cat by 2 minus lambda, and here you'll get minus h cat by 2 minus lambda. Here you'll get 0, here you'll get 0. This is okay, this is equals to 0. I'm going to start with vector spaces very soon, don't worry. Actually, there are a few things like, for example, diagonalization, which is also important. Although all these things are going to be repeated in vector spaces, because see, after all these things are going to be related to linear transformation there. So somehow I urge you to keep a little bit of patience, because once you keep patience, I'll start some other stuff in quantum mechanics, but like, for example, photoelectric effect, Compton effect on the other side, so that you don't get bored that entire day we are doing maths only. That I'll do. So this is how, this is from here you can clearly see this would be lambda square minus h cat square upon 4 equals to 0. So your eigenvalues would be plus minus h cat upon 2. So there would be 2 eigenvalues, and this is corresponding to spin up and spin down. So this is when we are going to see in quantum mechanics, we are going to see what I want to say. These corresponds to ms values. So I'm not getting into any of these things, but right now just think that there are 2 distinct eigenvalues to this, and corresponding to these 2 distinct eigenvalues, I want to construct eigenvectors. And what would be eigenvectors? It would be, so for example, if I'm using h cat by 2, then this would be 0, 0, 0 and minus. If I'm using h cat by 2, right? So if I'm using h cat by 2, what is the mistake that I've done? If I'm using h cat by 2, then it will be, okay, I'm not getting it. Why? What is the mistake here? Okay, just let me help myself for, okay, what is happening? Okay, so Sz, okay, so let us solve the eigenvector equation, right? So this is, sorry, so actually I should write it here. So I'm now trying to find the eigenvalue corresponding to h cat by 2. Okay, so what it would be? It would be simply Sz. What should I write? I should write x equals to h cat upon 2, and then I should write x here, right? This is how I should write. And I want to find this eigenvector x. So what it would be equals to? What is Sx? So Sx is, I think, Sx is h cat by 2. It is 0, and it is minus h cat by 2. Okay, and then I have this x. Let us write this x as x1 and x2, and here you have this h cat by 2, and here you have x1 and x2. Okay, Now try to find it. What it would be equals to? It would be equals to writing hk by 2, and here you have this x1, and here it is equivalent to writing minus x2. It would be equals to hk by 2, and then you have this x1, and here you have x2. Okay, I hope it is clear. And that implies what? That implies x2 must be equal to 0, right? That implies that is what I was getting there also. Okay, so that implies x2 is equal to 0, and x1 can be any real number. X1 can be any real number. So why not take x1 as simply r? Why not take x1 simply as r? So corresponding to this eigenvalue hk by 2, the eigenvectors would be, I think, 1 and 0. 1 and 0. I hope it is clear. Okay, one I have, look, I can also choose anything, but just to normalize it. Okay, and similarly, corresponding to lambda is equal to minus hk by 2, the eigenvectors would be 0 and 1. I hope it is clear. So I have done it for sz is equals to sz. You can do it for your what you can say. You can do it for your sx and sy as your homework. You can do that as a homework for you. Sx and sy, just try to find. I'm writing it here. They're also simple to find, don't worry. Just try to find the eigenvalues, eigenvectors corresponding to sx and sy. So corresponding to this sx and sy, also there would be eigenvalues, and correspondingly there would be eigenvectors. Try to find them as your homework. I think this would be your homework. Is that clear? Okay, now let us take another example for Hermitian matrices. Okay, now let us take another example from Hermitian matrices, and let us take a matrix of, a spin angular momentum. Let us take a matrix of spin angular momentum along a specific direction. Let's say along some direction, let's say theta comma phi, along some specific direction theta comma phi, and this is represented as, I'm writing Sn. So basically n cap. So n cap means we are trying to be in the direction of theta and phi, and this Sn is given by all these things I'm going to teach you. Don't worry. Right now I'm just taking them as an example here, so that it makes some sense of you can have some sense of physics behind it. Otherwise you will think that all maths is going. So cos theta, sin theta, and here you have e to the power minus of iota phi, and here you have sin theta, and here you have e to the power iota phi, and here you have minus of cos theta. Now this is a matrix of spin angular momentum along any direction theta comma phi, and this happens to be again a Hermitian matrix only. This happens to be a Hermitian matrix. Then you can see on your own also, because clearly Sn dagger, if you want to calculate, it will be h cat upon 2. Cos theta is a real entity, it will remain like this only. Sin theta e to the power iota phi, and then you will have sin theta e to the power minus iota phi minus of cos theta, and you have to take a transpose of it. So if you take a transpose, that then you will get h cat by 2. It would be cos theta sin theta e to the power iota phi. I think this is quite simple to see that this is a Hermitian matrix. This is a Hermitian matrix. So clearly this is a Hermitian matrix. Now we want to calculate the eigenvalues. So what would be eigenvalues? It would be cos theta, and you can multiply h cat inside, minus lambda h cat by 2, and then you will have h cat by 2 sin theta e to the power minus iota phi, and here you will have h cat by 2 sin theta e to the power iota phi, and here you will have minus h cat by 2 cos theta minus lambda, this mod, and this is equivalent to 0. This mod and this is equivalent to what? 0. I think minus was there somewhere. H cat by 2 cos theta minus lambda. I think I have made a mistake somewhere or what? H cat by 2. Okay, sorry, there is a mistake here. Okay, so this is this. Okay, and this will be, sorry, this will be simply this. Just give me a minute. Okay, so this will be like this. Okay, otherwise there will be a mistake. And this is h cat by 2 sin theta e ki power iota phi, and this is h cat by 2 sin theta e ki power iota phi. Okay, this is minus and this is plus. Okay, now if you want to calculate, what you will get? You will get, I think, this. You will get minus, if I take common, it would be h cat by 2 cos square, which is h cat square by 4. This is cos square theta, and this is minus lambda square. If you take a negative, and then things are easy to see, and this would be minus h cat square upon 4, and this would be sine square theta equal to 0. Now, if you you know that sine square theta plus cos square theta is 1, so you will simply get lambda square is equals to h cat square by 4, and in turn I can write that my lambda would be again plus minus h cat by 2. So there would be two distinct eigenvalues here, and corresponding to these two distinct eigenvalues, I'm going to have two distinct eigenvectors, and they're going to form a set of orthonormal eigenvectors. Let us see how. So corresponding to these two, you'll have this thing. So if I use this, use this h cat by 2, what I'll get? I know that my equation was h cat by 2 cos theta minus lambda, so it will be this. Then I had, I think, h cat by 2 sin theta e ki power minus of iota phi, and let us write the column vector to be x1 x2. I'm writing transpose here so that I can economize on the space. So this is one thing, and here you have sin theta e ki power of iota phi, and I think I had h cat by 2, sorry, h cat by 2 also would come here, and then I will have minus h cat upon 2, then I will have a cos theta and minus h cat upon 2, and then you have this x1 x2 written here, and this all equals what? 0. What does it imply? It implies that cos theta minus of 1 x1, this h cat upon 2 you can take common out, plus sin theta e ki power of minus iota phi x2 would be equals to what? 0. And similarly I can write here sin theta e ki power iota phi x1 minus cos theta plus 1 x2 would be equal to what? 0. So if you want to write what would your x1 and x2 would be, x1 would be, I think, x1 should I write as 1 plus cos of theta divided by sin theta e ki power iota phi x2, or you can write your x1 to be equals to this can be written as 2 sines, this can be written as 2 cos square theta by 2, this can be written as 2 sin theta by 2 cos theta by 2, so I'm directly writing it as tan theta by 2 e ki power iota phi x2. This is something that we are going to see in our quantum mechanics also, but just to give you a little bit glimpse of it. So your x1 would be tan theta by 2 e ki power iota phi x2. Okay, is that clear? So we write it in more better way. We actually write it in this fashion. So correspondingly to lambda 1, that is h cat upon 2, your x2 has come out as this. So what I do, I actually take cos theta 2, or I actually take what you can say, I'll take my cos theta x2 as simply, I think I should take it as cos theta 2. That would also do, right? Okay, there is a mistake. I think this should be cot theta by 2, right? Now this is cos square theta. Sorry, this would be cot theta by 2. Sorry, because you see, I will write my cos 1 plus cos theta is what it is, 2 cos square theta by 2, and if I write my sin theta, I can write it as 2 sin theta by 2 cos theta by 2. Okay, so it will be 2 sin theta by 2, and there would be cos theta by 2. So clearly it is cot theta by 2, right? It is cot theta by 2. So what I would do, I can do one thing. I can take my x1 as sin theta by 2. So I'll take my x1 as sin theta by 2. If I take my x1 as sin theta by 2, what will happen? If I take my x1 as not sin theta by 2, I should take cos theta by 2 then. Okay. If I take my x1 as cos theta by 2, then cos theta by 2 gets cancelled by cos theta by 2. अच्छा एक काम करते ना, I should write. Just consider this statement. What I want to say. See, I'm trying to write my x2 as tan theta by 2. There is some mistake on what, I don't know. What is the mistake? 1 plus cos theta divided by sin theta as e की power iota phi. So this will become e की power minus iota phi here. And my x2 can be written as tan theta by 2 into e की power iota phi, and I can write it as x1. So x2 would become tan theta by 2 into e की power iota phi x1, right? If I want to write my x1 as cos theta by 2, so if I write x1 as cos theta by 2, then I'm left with, I think, sin theta by 2 e की power iota phi. Okay, so this is how your eigenvector would look like. So for h cat by 2, your eigenvector would be cos theta by 2 sin theta by 2 e की power iota phi. Now let us try to find the eigenvector corresponding to lambda 2. What is lambda 2? Lambda 2 is minus h cat upon 2. So if I want to write corresponding to minus h cat upon 2, what it would be? So now let us again try to write the equation. So it was h cat by 2 cos theta plus h cat upon 2, because this is minus. Here you will get h cat upon 2 sin theta e की power minus iota phi, and then you have a h cat upon 2, and you have a sin theta here, and you have a e की power iota phi here, and then this is minus h cat upon 2 cos theta, and then plus h cat upon 2. This whole times a column vector, let's say x1 x2 equals to 0. Now let us try to find what it would be. I think it would be h cat, forget about h cat upon 2, you can take common out everywhere. So this would be cos theta plus 1 times x1 plus sin theta e की power minus iota phi x2 equal to 0. So from here, if you want to calculate your x2, so your x2, I'll calculate it now with all the caution. So x2 would be 1 plus cos theta with a negative sign, and then you will have a x1 divided by sine of theta, and then you have e की power minus of iota phi also here. Okay, so eventually I can write my x2 as minus of 1 plus cos theta is again, okay, 1 plus cos theta is again, I think I can write x2 as 1 plus cos theta is what? 2 cos square theta by 2, right? So I have to write something. I don't have space, right? Okay, so I'll solve it here. So another equation also let me write. Another equation would be sin theta e की power iota phi x1 minus of cos theta plus 1 x2 is equal to 0. Minus of cos theta plus 1 x2 is equal to 0. So now if I have to write my x2, what would be my x2? So if I have to write my x2 from here, just give me a minute so that I'll solve it for you. Okay, this is 1. And if I want to write what would be my x2, so let us try to find the x2 part. So what would be my x2? X2 can be written as, so let us write it in terms of x1 only, so that would be right. So let us write in terms of x1. So x1 is equals to 1 plus cos theta x2 divided by sine theta e की power iota phi. Or if you want to use this equation, I'm using it. This is what I have expressed my things into. So let me write it as x2 is equals to minus of 1 plus cos of theta x1 divided by sine of theta e की power of minus of iota phi. Okay, so what would be your x2? x2 would be simply minus of 1 plus cos theta is 2 cos square theta by 2, and this is 2 sine theta by 2 and cos theta by 2, and then you have this e की power iota phi, and then you have this x1. So eventually I can write my x2 as I think minus of cot of theta by 2 e की power of iota x1. Now if I want to write it in easier fashion, then I can do this way. And if I use this, I'll get certainly different answer. I'll get e की power minus iota phi. But actually, I preferred in the first eigenvector calculation, I preferred to have e की power iota phi. So therefore, I'm keeping a uniformity. So corresponding to this eigenvalue, the eigenvector would be, I think if I take x1 as sine theta by 2, then my second, this x2 would be minus of cos theta by 2 e की power iota phi. So I hope you've got in this particular lecture how to calculate eigenvalues and eigenvector for Hermitian matrices. In particular, we have taken two examples from the quantum mechanics, two examples from classical mechanics, and also we have discussed a good amount the properties. Probably from tomorrow we are going to take eigenvalues and eigenvectors for unitary matrices and a few questions, and then we'll conclude this chapter. I hope you're getting these lectures. If there is some doubt, there is some grievance, kindly let me know. I hope to meet you tomorrow. Till then, take care. Bye.